This is part 3 of the series Reasoning and Proof, and we're going to start this session with a little bit of an idea of counterexample. We talked last time about a counterexample being an example that disproves a conjecture. So that's the definition of a counterexample. And what you're going to be doing when you look for counterexamples is you're going to be looking for something that disproves whatever you're being told. So for example, if I say all dogs have 4 legs, you're looking for an example that disproves that conjecture. And if you happen to know somebody named Jennifer whose dog had a tragic accident and now only has 3 legs, then that dog would be a counterexample which disproves the conjecture that all dogs have 4 legs. More practically, let's take a look at a different type of an example. Here we're given a conjecture that the product of 2 integers is a positive integer. In other words, what this is trying to say is that the product of 2 integers is always going to be a positive integer. You're looking for an example where that's not true. So always think about the conjecture that you're being given. You're being told this is always going to be true. You're looking for something that disproves that idea. So the product of 2 integers is a positive integer. Well, this is a fairly simple one to find a counterexample for. Let's take the integer 2, and product means multiply, and let's take -1. These are 2 integers because an integer doesn't have to be positive. It can be positive and negative, is -2. So this product of these 2 integers is negative, so this would be a specific counterexample which proves this conjecture incorrect or false. It's all it takes is one example to disprove a conjecture. Alright, let's try one more. In this one, we're being told that the product of 2 integers is always greater than either of the 2 integers. So the product of 2 integers is greater than 2 integers. Well, here again, we can take the value 2, and we're looking for something where this is true, where this is not true, where the product of 2 integers is not greater than both integers. Well, if I multiply 2 by the value of 1, 2 times 1 is just 2, and 2 is not greater than either of these 2 integers. It's equal to, therefore this would be a counterexample that disproves this conjecture. So once again, that's all you're trying to do with these conjectures, is you're trying to show one example that proves that conjecture false. Sometimes it's a little tricky, but this is the general idea. Now let's move in to perhaps the largest idea in reasoning and analytical reasoning specifically that is used constantly and consistently in geometry especially. The idea at hand here is deductive reasoning. Deductive reasoning is reasoning using definitions, properties, and laws of logic to build a logical argument. So anyone who's ever read or watched a detective story and has heard of the name Sherlock Holmes. Sherlock Holmes is Arthur Conan Doyle's arguably the greatest logical reasoner of all time. His primary premise was deductive reasoning. He would take minute clues and observations and he would put them together to build logical arguments that went from beginning to end to develop this logical chain to lead you to who was the culprit or what had happened in this particular situation. This is distinctly different than just simple inductive reasoning, which simply looks at a few isolated examples and tries to draw a general conclusion. So deductive reasoning is specifically using specific facts, properties, and laws of logic to build a logical argument. Now, there are 2 fundamental logical laws that we're going to employ in using this deductive reasoning capability. The first one is the law of detachment. The law of detachment simply says, if the hypothesis of a true conditional is true, then the conclusion is true. Now this sounds fairly simple on the surface, but a lot of people get twisted in knots by this one only because the terms are a little bit strange and it appears a little bit cryptic. So what I'm going to do to introduce this is an example that highlights some of the deficiencies people make when they're exercising this idea of law of detachment. We'll start with this simple conditional statement. If I work, then I make money. Now let's assume that this is true. So if I work, the I work part is the hypothesis, I make money is the conclusion. We're going to assume that this conditional statement is true. That is, if I work, then I in fact will make money. Now we take some statement of fact. I worked 8 hours today. Now the first thing to note is this statement is referring to the hypothesis. It's talking about working. It's not talking about making money. So that's the first piece. The law of detachment says if the hypothesis of a true conditional is true. So this statement is telling us that the hypothesis of this conditional statement is true. If that is the case, if this is a true conditional, and we have a statement saying that the hypothesis is true, then and only then can you conclude the conclusion of that true conditional is true. So if you're asked, given this statement and this fact, what can you conclude using the law of detachment? You would say, I make money. Just that simple. You wouldn't repeat the if then. You wouldn't say any of that. You would simply say, I make money. The thing that you can conclude is that the conclusion is true because the law of detachment applies. Once again, this fact told us the hypothesis of a true conditional was true, therefore the conclusion must be true. Now the mistake that people make is, as we referred to previously, they try to interpret these statements in raw form in English and try to make sense of them. So I would like to show you something that will hopefully clear up this situation. Now here we have another conditional statement. If Glicknicht, then Buglump. Now, on the surface you might chuckle and go, that doesn't make any sense. Precisely. Don't worry about whether or not this is true or whether it makes sense. Just know that we only need to know that this will happen if this is true. Here is your hypothesis, Glicknicht, whatever that is, who cares, it doesn't matter. Then Buglump will happen, whatever that is. We don't care what it is. If this is true, then this must be true. Now let's take a look at a fact. Here we have a fact. It says tonight is Glicknicht. Well, clearly this is pointing to the hypothesis, and it's saying that this is true somehow. And because of that, this statement is telling us that the hypothesis is true. Therefore, given this conditional, if we're assuming that the conditional is true and this fact, what can we conclude? We can conclude Buglump. Whatever that is, it doesn't matter what it is. We're looking at the form, not the substance of it. So whatever the hypothesis is, that has to be true. So this is telling us the hypothesis is true. Therefore, the conclusion must be true if the hypothesis is true of this true conditional. That is where the law of detachment applies. Now let's look at a case where it doesn't apply. This fact says, tonight is Flanslat. Well, clearly, this is not referring to this piece or this piece. This is not telling us that this is true. If this fact does not tell us that the hypothesis is true, then according to the law of detachment, we cannot conclude anything. So the fact that this is not true, we're not being told that this is true, means we cannot assume that this piece is true. That is the essence of law of detachment. We can only use the law of detachment if the fact we're given tells us that the hypothesis of a true conditional is true, and the only thing we can conclude is that the conclusion is true. So let's look at one final example, and hopefully you'll have this down. The conditional statement says, if two segments have the same length, then they are congruent. We would classify this as a true conditional statement. This is basically the definition of congruent line segments. The fact is length of segment AB is 5. The length of segment CD is 5. Using the law of detachment, what can you conclude? Well, this is telling us that we have two segments that have the same length. So this is telling us, this fact tells us the hypothesis of this true conditional is true. Therefore, by the law of detachment applies, and we can say they are congruent. You could go further and say segment AB is congruent to segment CD, but that's all you really need to say is they are congruent. The segments are congruent, however you want to say that. But given this statement and the fact that the hypothesis is true, we can conclude the law of detachment applies and the conclusion is true. All right, let's move on to the next law of logic, which is called the law of syllogism. Now, a syllogism in English is a logical statement consisting of two conditional statements, one with a major premise and the other a minor premise, that leads to a third logical statement, a conclusion. Now, this may sound complicated, but when I give you an example, it'll be really, really straightforward. In this example, if you study, then you will pass the test. If you pass the test, then you will be happy. Therefore, if you study, then you will be happy. So you can see that this is the major premise, this is the minor premise, and this statement followed by this statement leads us to the third statement. Now that brings us to the law of syllogism. And with the law of syllogism, it talks about this order of events. And it says, given two true conditional statements in which the hypothesis of the second is the conclusion of the first, then a third logical statement can be made using the hypothesis of the first. The hypothesis of the first becomes the hypothesis of the third, and the conclusion of the second. Conclusion of the second becomes the conclusion of the third. So if you study, then you will pass the test. This piece goes down here. If you pass the test, that leads to you being happy. Therefore, if you study, then you will be happy. If you study, then you will be happy. Logically, the statement is given as if P then Q, if Q then R. So you can see that we start with a hypothesis, which leads to a first conclusion. That conclusion becomes the hypothesis of our second statement. That hypothesis leads to a second conclusion. Therefore, the first hypothesis leads to the second conclusion. This ellipsis, this is called an ellipsis. This means therefore. Now there are a few more things that we need to cover with the law of syllogism, so we're going to go ahead and do that in the next video. So please look at the next video and I'll talk to you then.